It began with a sudden blackout. An entire hospital plunged into darkness as every conventional backup failed. Patients' lives hung in the balance, monitors were silenced, and operating rooms went cold. In that moment, desperate engineers proposed the unthinkable, wiring a massive locomotive directly into the hospital's heart. But locomotives aren't built for this. The consequences of failure were not just inconvenient, they were fatal. How did a train engine become the last hope to save the lives inside? In the instant the lights vanished, the hospital was stripped to its essentials: steel, glass, and the people inside. In the intensive care unit, ventilators fell silent, replaced by the anxious breathing of patients and the hurried footsteps of nurses. Monitors that once blinked with steady reassurance now glowed only with the faint light of battery backups, ticking down the minutes before total darkness. Surgeons, mid-procedure, found themselves frozen mid-incision, hands poised above patients, as the hum of operating room machinery faded. The air, once filled with the steady rhythm of pumps and beeps, became thick with uncertainty. Hallways, usually bustling, turned into shadowy corridors, lit only by the dim emergency exit signs. Staff moved quickly, checking on patients whose lives depended on machines that had seconds, maybe minutes, of battery left. In the neonatal ward, incubators grew cold. Oxygen concentrators running on backup batteries ticked closer to empty. For some, the choice was stark: evacuate and risk the dangers of transport, or stay and hope for a miracle. Standard protocols offered little comfort. The hospital's emergency generators, designed to roar to life within 10 seconds, stayed silent. In the mechanical room, engineers worked by flashlight, tracing wires and flipping switches, searching for the cause. Fuel levels were checked and rechecked. Transfer switches, meant to automatically reroute power, had failed, possibly jammed by a surge or a relay burnt out from years of neglect. Outside, the storm raged on, making any delivery of replacement parts or portable generators nearly impossible. The usual safety nets were gone. Battery backups, meant only as a bridge until generators took over, began to fail one by one. Medical teams triaged by flashlight, prioritizing those whose lives depended most on electricity. Communication systems faltered, with pagers and intercoms reduced to static. In the pharmacy, temperature-sensitive medications faced spoilage as refrigeration failed. Every department felt the pressure, from radiology to the blood bank, as the hospital's intricate web of systems unraveled. In moments like these, the difference between life and death narrowed to a matter of minutes. The hospital, a place built for certainty and control, had become a battleground against chaos. Staff improvised, using manual resuscitators and hand-cranked beds, but the scale of the crisis was overwhelming. With no clear solution and time slipping away, desperation crept in. The question was no longer how to restore comfort, but how to keep people alive until power could be restored by any means necessary. Every second without power brought the hospital closer to catastrophe. In the intensive care unit, nurses huddled around bedsides, counting down the minutes left on battery-powered ventilators. The clock above the nurses' station, usually ignored, became a silent threat. With each passing minute, the margin for error shrank. For some patients, those on life support and those in the middle of surgery, there was no backup plan. The batteries that kept their machines alive were rated for only 20, maybe 30 minutes. Already their charge was slipping away. Down in the basement, the chief facilities engineer mapped out the remaining time for each critical system. Oxygen concentrators would drop offline in less than 15 minutes. Neonatal incubators, already losing heat, had less than 10 minutes before temperatures would fall to dangerous levels. The pharmacy's refrigeration units, holding essential medications and blood products, were not far behind. The hospital's emergency lighting, powered by its own battery banks, flickered as the load increased and the reserves dwindled. The engineer knew the hospital's electrical system inside and out. But the challenge now was not just restoring power. It was finding a source, any source, that could deliver the right voltage and frequency quickly enough to matter. The team faced a technical mismatch. The hospital's wiring demanded 480-volt three-phase alternating current at 60 Hz. Most portable generators were either too small or could not be delivered through the storm. Even if a locomotive could be brought close, its output would be all wrong. Direct current at high voltages, or variable frequency alternating current meant for traction motors rather than sensitive medical equipment. Connecting the wrong kind of power could fry life-saving machines or spark fires in the walls. The pressure mounted with every system that dropped offline. Staff tracked the time left for each patient on a whiteboard, updating numbers as battery indicators flashed red. The engineer's radio crackled with questions. How much longer for the operating room? How much longer for the neonatal intensive care unit? He had no good answers. The hospital's backup protocols were never designed for a failure this complete, or for a solution this unconventional. Every option was weighed against the time it would take to implement, and the risk of causing more harm than good. In the chaos, the engineer made a decision. If there was any hope of using the locomotive's generator, the team would need to solve the technical mismatch quickly. Transformers, converters, and isolation equipment would have to be assembled on the fly. The hospital's electrical panel, never meant for such an experiment, would become the gateway between two worlds: the raw industrial power of a train engine and the delicate life-sustaining circuits of a modern hospital. The countdown continued, measured not just in minutes, but in heartbeats. A diesel-electric locomotive is, at its core, a rolling power plant. The heart of the system is the prime mover, a massive diesel engine, often a V12 or V16, with a displacement that dwarfs most truck engines. When running at full throttle, these engines can generate between 2,000 and 6,000 kilowatts of mechanical power, depending on the model. This energy does not drive the wheels directly. Instead, it spins a generator, typically producing high-voltage direct current, or, in newer locomotives, three-phase alternating current. That electricity is then fed to traction motors, which actually turn the wheels. For scale, a single modern locomotive can deliver as much as 4 to 6 megawatts of electrical output, enough to power a small neighborhood. By comparison, a typical large hospital's peak demand might range from 3 to 10 megawatts, depending on the number of operating rooms, imaging suites, and intensive care beds. Even a mid-century locomotive, like the EMD F series or Alco RS models, could produce over 1,500 kilowatts, roughly matching the emergency load of a medium-sized hospital. But the numbers alone do not tell the whole story. The power generated on a locomotive is designed for one purpose: to move thousands of tons of freight over long distances, not to run delicate medical equipment. The voltage is often far higher than what a hospital's systems are built to handle, and the current may be direct or variable frequency alternating current, depending on how the locomotive is configured. Hospital electrical systems, on the other hand, rely on tightly regulated 480-volt, three-phase alternating current at a fixed 60 Hz. That is the standard for critical medical loads. MRI scanners, ventilators, surgical lights, and climate control systems all depend on that steady, predictable supply. Matching a locomotive's raw output to a hospital's needs is not as simple as running a cable from one to the other. The hospital's load is not just about total wattage. It is about stability, frequency, and the ability to handle sensitive electronics without surges or interruptions. Any mismatch, too much voltage, too much harmonic distortion, or a sudden spike, could damage equipment or put patients at risk. Still, the sheer capacity of a locomotive makes it a tempting source in a crisis. With a properly tuned engine and the right conversion gear, it is theoretically possible to regulate the frequency and voltage to match hospital requirements. In some emergencies, railway engineers have demonstrated that a locomotive, set to a constant engine speed and isolated from the traction motors, can be coaxed into producing a stable 60 Hz output. But this requires careful adjustment, constant monitoring, and a deep understanding of both rail and hospital electrical systems. The challenge is not just about scale, it is about precision. The locomotive's generator can deliver the raw power, but making it safe and usable for a hospital's life support systems demands a new layer of engineering. Transformers, frequency converters, and isolation relays all become part of the equation. The next step is finding a way to bridge that gap, turning the brute force of a train engine into the lifeline for a hospital on the brink. In the yard behind the hospital, the ground was slick with rain and littered with branches. The operations supervisor from the rail company stepped out of his truck, boots sinking into the mud, and surveyed the narrow access road that ran alongside the hospital's service wing. Getting a locomotive anywhere near the building was never part of the original design. But with the hospital's backup generators silent and the city's grid crippled, improvisation was the only option left. The call went out to the nearest rail terminal for a diesel-electric engine with enough output to match the hospital's emergency load. Within the hour, a CN crew was rolling out locomotive number 3502, a workhorse model familiar to anyone who had spent time along the Quebec main lines. The engine, weighing over 120 tons, was uncoupled from its train and, with permission from dispatch, slowly inched along the spur line closest to the hospital. At the last possible switch, rail workers threw the points by hand, guiding the locomotive off the main track and onto the short siding that ran behind the property. Spotting the engine was a job that demanded precision. The supervisor walked ahead, radio pressed to his ear, relaying instructions to the engineer in the cab. Each meter mattered, too close, and the hospital's loading dock would block access for the electrical team. Too far, and the heavy gauge cables would not reach the main switchgear panel. The locomotive was brought to a halt, with its generator bay aligned to the hospital's electrical room. Air brakes hissed. The engine idled, sending a low vibration through the rails and the wet ground beneath. With the locomotive in position, the next challenge was bridging the physical gap between rail power and hospital circuits. The electrical team unspooled reels of 4/0 copper cable, thick as a man's thumb, each length rated to carry hundreds of amps without overheating. Insulated gloves and arc-rated suits were mandatory. The cables were threaded through temporary cable trays, crossing the slick pavement and up into the building's service entrance. Every step required coordination. One slip, one stray tool, and the entire system could short or worse. At the hospital's main electrical panel, the crew installed a manual transfer switch. This device, a steel box the size of a small refrigerator, allowed engineers to isolate the hospital from the dead city grid and connect directly to the locomotive's output. The switchgear was rated for the full emergency load, with built-in overcurrent protection and visible disconnects. Before any connection was made, the lines were checked, tagged, and grounded. The operations supervisor double-checked every lug and terminal, barking out confirmation as each phase was landed. Back at the locomotive, the engineer adjusted the throttle, holding the prime mover at a steady RPM. The generator was configured for 60 Hz output, matching the hospital's requirements as closely as possible. A portable isolation transformer craned in from a nearby utility yard was wired in line to step down the voltage and filter out any surges. The cables were clamped to the locomotive's export terminals, each connection tightened with a torque wrench and checked for stray voltage. The final step was a coordinated sequence. The hospital's emergency circuits were isolated, the transfer switch set to external, and the locomotive's generator brought up to speed. The supervisor gave the all-clear. For a moment, there was only the sound of rain on steel and the low rumble of the diesel engine. The bridge between rail and hospital was complete, raw, improvised, but ready. Everything depended on what would happen next. A low mechanical rumble cut through the silence as the locomotive's prime mover throttled up, sending a surge of power down the thick copper cables. In the hospital's main electrical room, indicator lights blinked from red to green, one by one. The transfer switch clunked into place. At first, nothing happened. Then, with a flicker, the fluorescent lights in the halls snapped back to life. Monitors restarted in the ICU, their screens filling with vital signs that had been lost minutes before. The steady whir of ventilators returned, pushing air into the lungs of patients who had been teetering between hope and disaster. On the surgical floor, overhead lights illuminated the operating tables again, letting surgeons resume their delicate work without missing a beat. In the neonatal ward, incubators warmed, their displays showing safe temperatures for the smallest patients. The pharmacy's refrigerators hummed, preserving critical medications that just moments before had been in jeopardy. Nurses exchanged glances, some letting out the breath they'd been holding, others blinking back tears of relief. A wave of cautious optimism swept through the building. The hospital's public address system crackled, then cleared. An announcement came over the speakers. Power has been restored to critical systems. For a moment, the only sounds were the return of machinery and the distant, rhythmic throb of the locomotive outside. Staff moved quickly to check every ward, confirming that life support, alarms, and communication lines were functioning. The crisis was far from over, but for the first time in hours, survival no longer depended on improvisation alone. The hospital had a lifeline, powered by a machine never designed for this purpose, but now carrying the weight of every life within those walls. The story of a hospital running on the muscle of a locomotive stands as more than a one-off feat of improvisation. It draws from a longer tradition of crisis engineering, where necessity pushes people to rethink what is possible. During World War II, hospital trains in Europe faced similar challenges, caring for hundreds of wounded soldiers far from stable infrastructure. Those trains carried their own diesel generators, not relying on the locomotive up front. But the principle was the same. When fixed systems failed, mobility and ingenuity kept the lights on. Today, that legacy shapes how emergency planners prepare for the unknown. Modern protocols recommend not just redundant generators, but also portable transformers, heavy-duty cabling, and detailed single-line diagrams for every critical facility. After action reports from events like the 1998 Quebec ice storm, when a CN locomotive powered Boucherville's City Hall, now serve as case studies in engineering journals and disaster response workshops. Researchers and policymakers stress the importance of archiving technical logs, maintenance records, and even minute-by-minute decision notes, so that future teams can retrace every step. The lesson is clear. Resilience depends on both preparation and the willingness to improvise with what is at hand. For hospitals, that means treating every crisis as a chance to refine protocols, invest in flexible systems, and document what works, so the next emergency finds people ready, not just hopeful. Today, hospitals still face power grid threats, from climate events to cyber attacks. No locomotive has ever powered an entire hospital, but the idea underscores our dependence on resilient infrastructure and creative crisis planning. As technology evolves, true readiness demands solutions no one's imagined yet. The next emergency won't wait for tradition. What unconventional backup would you trust if the lights went out? Share your thoughts below.